I looked at roughly 44,000 food delivery orders and found that nearly 30% of them didn't reach customers on time. That's not a small rounding error. That's almost 1 in 3 orders failing its own delivery promise. This project is about figuring out exactly where those failures are coming from. Hey guys, my name is Chandan Sahu and I have built this food delivery operations analytics dashboard project. Let's look at it. The dataset comes from Kaggle. It's a Zomato delivery operations dataset with around 43,000 records. Each row represents one delivery order, and it includes things like how long the delivery actually took, what the traffic was like, what the weather conditions were, which city tier the order came from, and the delivery partner details. Quick note on terminology. When I say SLA breach, I mean any delivery that exceeded the expected delivery threshold set in the dataset. I will be using the term throughout, so I wanted to define it upfront. Here's what the project is built on. Python with Pandas and NumPy for cleaning the raw data, PostgreSQL for structured operational queries, and pgadmin to look upon the outcome in the GUI, Matplotlib and Seaborn for the EDA analysis, Power BI for the final dashboard, and Git and GitHub for version control. Before any analysis could happen, the raw data needed a fair amount of work. There were missing values in delivery person age and ratings. Weather and traffic columns had inconsistent labeling. The same category written different ways across different places. Several columns had the wrong data types, and the order timestamps were stored as strings, so those needed to be converted into actual date-time format. I dealt with each of these systematically. Numeric columns like age and rating were filled using median values. Categorical columns like weather and traffic density were filled using the mode. Rows where the core time columns were null, those were dropped entirely, since without timestamps there's nothing useful to analyze. After cleaning, I built out a few derived columns that power the entire analysis downstream. The most important one is the SLA breach flag, a simple true-false column that marks whether a delivery exceeded the 30-minute threshold or not. I also extracted the order hour from the timestamp, calculated the actual delivery duration, and created a delivery speed category, which are fast, on time, late, or very late. These engineered features are what make the SQL and dashboard work. Clean data isn't glamorous, but skipping this step properly would have made every finding after it unreliable. With everything loaded into Postgres, I ran a series of queries to break down where breaches were actually happening. Firstly, across 44,000 orders, the overall SLA breach rate came out around 30%. About 13,000 deliveries arrived late. That's the number everything else gets measured against. Under traffic jam conditions, the breach rate jumped over 50%. 1 in 2 deliveries was failing during congestion, and here's what made that number more serious. Traffic jam was also one of the highest volume traffic categories with nearly 14,000 orders. So this isn't an edge case, it's a core operational problem. Weather told a similar story. Cloudy and foggy conditions both came around 43 to 44% breach rate, significantly higher than sunny weather, which is around 12%. The city tier breakdown was probably the most striking finding structurally. Semi-urban areas had a 100% breach rate across 156 orders. Every single semi-urban order failed SLA. Metropolitan areas were at 32.7% and urban at 18.6%. It's worth being careful with that 100% figure. 156 orders is a small sample, so I wouldn't overstate it, but the direction is clear. Semi-urban delivery is structurally broken in this dataset, and that's a network problem, not a weather or traffic problem. Putting it all together, the biggest drivers of SLA failure in this dataset are traffic congestion, semi-urban network gaps, weather conditions, and the evening demand surge between 8 to 10 p.m. The SQL gave me the numbers. The Python visualizations made the patterns easier to interpret. Starting with traffic, the bar chart shows breach rates climbing steadily from low traffic at under 8% all the way up to jam conditions crossing 50%. The color coding makes the risk gradient immediately readable, green to red, low to critical. The weather chart shows the same kind of pattern. Cloudy and foggy conditions are clearly in a different risk category compared to sunny or any other weather condition. And the chart on the right shows average delivery time by weather. Both fog and cloud are pushing close to 30-minute SLA threshold on average, which explains why breach rates are so high under those conditions. The city tier comparison is hard to ignore. Semi-urban is highlighted in red for a reason. Metropolitan is just above the overall average. Urban is well below it. The performance gap between city types isn't small, it's structural. This is the heat map. SLA breach rate by hour of day and day of week. The lighter cells are higher breach rates. If you look at the columns around hour 19 to 21, that's 7 to 9 p.m. You can see those cells are consistently lighter across almost every day of the week. The evening dinner window is a systematic risk, not a one-off. The dashboard was built to make these findings accessible to someone who doesn't want to read SQL output. The order volume by traffic density chart is important here. It shows that jam conditions aren't just the most dangerous, they are also one of the highest volume categories. That combination is what makes it the top priority, and the city tier bar chart on the right makes semi-urban underperformance immediately visible. On the delivery performance page, I have applied the traffic jam filter and cloudy weather filter together to show the worst case scenario. Under those combined conditions, breach rates across vehicle types all land above 70%. The average delivery time chart in the bottom right shows deliveries consistently exceeding 36 minutes, which is more than the 30-minute SLA threshold. The analysis pointed to 3 concrete areas where the operations team could act. First one is festival surge protocol. Festival days must be treated as separate operational mode, where pre-positioning of additional delivery partners 2 hours before peak, enforcing dynamic pricing to suppress low priority orders and set the customer SLA expectations to 45 minutes rather than 30 minutes. Second one is semi-urban capacity planning. Semi-urban zones need dedicated partner allocation models. Current partner density is insufficient for order volume, where we have to use geo-cluster semi-urban orders and assign dedicated partner pools rather than sharing with urban supply. And the third one is evening demand surge staffing. The 8 to 10 p.m. window requires mandatory surge staffing. We have to incentivize partners' availability between 7 to 10 p.m. through guaranteed minimum earnings, reducing the gap between order demand and fulfillment capacity. This project is documented and publicly available on GitHub. Thanks for watching.